This is a coffee brief video from the Ohio State University Astronomy Department summarizing our recent paper, The Cepheid Distance to the Maser-Host Galaxy NGC 4258, Studying Systematics with the Large Binocular Telescope. I'm Michael Fausnaugh, a graduate student here at OSU. The Large Binocular Telescope, or LBT, is currently executing an observing program targeting luminous variable sources in 25 nearby star-forming galaxies. In this work, we search this data set for pulsating Cepheid stars. Cepheids are important distance indicators because their absolute magnitudes can easily be determined from their pulsation periods, and they are luminous enough to serve as useful links between the local distance ladders and more distant standard candle. One of the galaxies in the monitoring program is NGC 4258, a galaxy for which a precise 3% geometric distance has been determined. Because of this precise distance, NGC 4258 is one of the primary distance anchors for local measurements of the Hubble constant, and it is therefore extremely important to understand the systematic effects influencing measurements of the Cepheid distance to this galaxy. In this study, we study three such systematics: treatments of extinction, variations in the extinction law, and metallicities of the Cepheids, although I only discuss extinction and metallicity in this video. We identify a new sample of Cepheids in NGC 4258 using LBT data gathered between 2008 and 2013. Using image subtraction and the empirical light curve templates of Peja and Kachanik 2012, we are able to identify and accurately phase 94 Cepheids over the 5-year baseline of LBT data. While image subtraction allows us to identify Cepheids by detecting their variability, the LBT images are far too crowded to measure the mean magnitudes of the Cepheids directly. After identifying the Cepheids using differential LBT light curves, we calibrate their mean magnitudes using higher resolution archival B, V, I, and H band Hubble Space Telescope images. Of our initial 94 Cepheids, we are able to match 43 in HST images, and we use 40 of these matched Cepheids in our final sample. Next, we estimate the Cepheid mean magnitudes by combining information about their periods and phases from LBT light curves with the matched HST data. Example light curves are shown here, where the black points represent differential LBT data and the large red points are HST calibration measurements. Finally, we make use of several models based on period luminosity relations for Cepheids in the Large Magellanic Cloud, or LMC, to describe the Cepheid mean magnitudes and relative distance between the LMC and NGC 4258. In our first model, we take the standard approach of many Cepheid studies, wherein we adopt a Cardelli, Clayton, and Mathis 1989 extinction law and set the ratio of total to selective extinction R sub v equal to 3.1. We then solve for the individual extinctions of each Cepheid, and the results are shown in this figure. The vertical axis shows the extinction-corrected mean magnitudes, where m hat sub f is the apparent mean magnitude in filter f, E sub I of b minus v is the individual reddening of each Cepheid, and R sub f is the ratio of total to selective extinction in each band, calculated from the extinction law. The dashed lines show the root mean square scatter of the data about the model, and it is important to note that our model absorbs all variations allowed by the data that can be described by extinction, which results in the low scatter visible in this figure. An alternative way of visualizing this is through the projected residuals of the data from the model. With 4-band photometry, there are 6 such projections, each shown here in a separate panel. The dashed lines represent variations that can be modeled as extinction, and the data do not admit any correlations in this direction. However, based on a principal component analysis, we find that there is a single preferred direction of the residuals, represented by the solid line. The emergence of this principal component is related to the Cepheid colors and can be explained by a grayer extinction law, a color-dependent metallicity correction, or some other systematic effect. See our paper for details. We also estimate the impact of Cepheid metallicities on the determined distance. We use the radial position of the Cepheids inside of NGC 4258, coupled with oxygen abundance gradients available in the literature, as a proxy for metallicity. In this figure, we show the distribution of the distance modulus, delta mu sub LMC, and metallicity correction gamma sub 1, estimated by 10,000 bootstrap resampling trials of the fitting procedure. The left panel shows the results using our final sample of 40 Cepheids, while the right panel shows the results for 120 Cepheids, obtained by combining the LBT sample with BVI photometry of 80 Cepheids found in a previous study. The different colors represent different metallicity scales, and the points represent the medians of the distributions. While the LBT Cepheids alone do not show any evidence for a metallicity-dependent adjustment to the distance, the combined sample yields a detection of minus 0.6 mag per dex at about the 2.9 sigma level using the metallicity system of Zaritsky et al. 1994. After combining our ensemble of models, We estimate that the relative distance between the LMC and NGC 4258 is 10.83 magnitudes, which places the LMC at 51.8 kiloparsecs. A conservative estimate of our uncertainties results in an error of 6%. Thank you for watching this coffee brief. For more information and results, please consult our paper posted on AstroPH this week.